Okay, so let's continue our lecture. Okay, previously we were talking about the tire coding. So we showed the one of the example, which we used the 1000 state random walk as an example to show this the better performance in the tire coding compared to the state aggregation, right? So as you can see here, the state aggregation is a special case, means that it only has one tiling, and the green colored lines is the tile coding with 50 tilings. Okay, then with these 50 tilings, that actually it outperforms the state aggregation in the average value error. So now we move to another basis function, which is radial basis function. Radial basis functions is like a generalization of code coding to the continuous valued features. So since if you look at the feature of the previous one, in the tire coding, usually, for example, here, when we have these four features, four tires, actually the four tires will be binary, either 0 or 1. So, but it may lose some resolution when the space become continuous. So in that case, we can use this radial basis function, because actually we can represent any number between 0 to 1 that can reflect different degrees of a feature. Okay, typically an RBF feature has a Gaussian response, XIS, depend only on the distance between the states. Okay, distance between the states, and the features protopical or centric states, CI. Okay, the equation for defining this feature is shown below. The XIS equals the Gaussian distribution shape. Okay, the Bayer shape. Then we have this S minus the CI is the central point, right? It's, if you remember the Gaussian distribution, the CI, it defines the average value of the Gaussian distribution. And also it depends on the sigma. Sigma I will define the narrow, or whether it's a wide or narrow of the Bayer shaped the distance, right? So if you look at the center, it is the one-dimensional this RBF with Euclidean distance, as you can see in the center. So if you look at here, CI is one central state. Then we just mirror the state, the value of the state to the center state, and they can have continuously the value in this range. Okay. So let's continue. Yeah, I put these slides here again to just to remember you about the why we learned all those linear methods. So since we are defining this value function as a parameterized with a weight, the weight vector, okay, then we can rewrite this because since it's a linear function, so W was transposed as a column. Now we transpose it back again, become a raw vector, then times a column, which is a feature vector, XS. So since it's a linear function, then we can directly write into the linear shape of this function. So this XS is called a feature vector. Then each element in this XS is a feature of S. So for constructing this xi, we have been learning all those basis function, right? For example, here, previous xis, the RBF-based basis function, this function, then we can just put this this RBF feature to here to replace this part, then it become an RBF basis linear method. Okay, that's how you can apply those methods to this SGD. Now we move to another topic, which is related to select step size parameters manually. So in the previously, when we learned the tabular methods, sometimes we set up a step size alpha to a constant value 1. If you remember, when we define those the learning step, most of the time we just use 1, right? And at the beginning, when we learned the multi-arm banded problem, the alpha is set to the size of the step we are running, like 1/n. So now, actually, in other cases, alpha is set to be 1/tau. Here we use tau instead of n. So here, the tau is the size of experiences, like the steps in the map problems, or the steps in the Monte Carlo methods. So in like step in each episode. Okay. In this case, actually, we are slow down the learning speed to like each step. We only learn very small part of actually each step we only learn a small part of approximation. So similarly, in this linear SGD method, we can set alpha to be a value related to tau. So mostly we can define alpha equals actually there is a actually it's the fraction, right? So it's 1/tau times the expectation of the feature space, feature vectors, the product of feature vectors. So it's like we just make a product of the feature vector. So X is a random feature vector chosen from the same distribution of the input vectors in the SGD. So yeah, we may later look at some example about this definition, this kind of a small technique. Okay. Okay, so far we have been talking about the linear method. So for using, as I put our goal here, when we define our state value function, we use a linear approach. Then we can make it expand it become a linear form. So we just each feature is weighted by a weight vector, the coefficient. So with this way, actually we just use the SGD to update the weight vector to approximate the weight vector, then to minimize the value error, right? The VE bar. So iteration. So when we run the like Monte Carlo method or TD0 method, then those weight can be minimized. So, but actually this linear method is okay, but in some it still has some limitation because the one thing is it may, for some complicated environment or some complex behavior and state space, it may not have a good expressive power. So that's why recently, in recent years, like the nonlinear function approximation method has been kind of become attractive to the researchers and engineers in this area. Especially we are using the artificial neural networks. Here is a simple feed-forward neural networks example. As you can see here, actually it is a 2 layers neural networks. So we have a 1 input layer, which has a 4 input units. And we have one output layer with 2 output units. And inside, between the input and output, we have 2 hidden layers. Then the connection between them are the weights. which we need to optimize. And all those the units or nodes in the two hidden layers are representation of the input units. Okay, so the reason we can say that this neural network is a nonlinear function approximation in our case, because in the inside of the two hidden layers, we put the nonlinear function, also called activation function, to extract some feature, some a set of features from the input that may be useful for us to differentiate some information. Okay, so this is feed-forward neural networks. So generally, when you define neural networks, then we need to, our goal is to, similar to the linear case, we also need to want to update the weights. So to minimize the so-called loss function. Loss function is similar to the let's say target function in the linear case. So but loss function is, yeah, there are more ways to define loss function in the neural networks. So let's take a look at the single unit in the neural networks. If you remember, I guess most of you have already learned this deep learning stuff. So for a single unit in the neural networks, you have multiple inputs to contribute to this node, and this input, the link, represents a weight. So inside of this node is a linear combination with bias or regulation part. With this linear combination, then you put them into an activation function. This fz is the activation function. So because of this activation function, it brings some nonlinear relationship between input and output. So then we have this output. The output will have some extracted feature information from those input if those weights have been updated. Okay, so if we, so the left-hand side is a single unit in neural networks. So right-hand side is a tire coding. Actually, we can have some comparison here. If you look at the tire coding, so in the tire coding, our setting is that we consider a 2D space. In a 2D space, we use multiple tilings to represent states, right? For example, if we have one state, then it may be covered by the 3 tires, right? 3 tires. And then the output is a binary. We just give 1 to those 3 tires. Instead of in other tires, we just give 0, because only those 3 tires will be related to a particular state. So it's kind of we use those 3 tires to be the feature of the input. So if you compare this to the unit in the neural networks, instead of using this binary or linear combination, actually since we are introducing an activation function, actually the output become more complicated, more complex. And yeah, so if we look at yeah, we may take a look at it later. So let's first move on. So then activation function in neural networks, as I guess you already knew all those functions like logistic function, ReLU function, 10H function. So logistic function is defined in this way, okay? It's also called sigmoid, and it generates it's kind of this kind of shape to generate the range from 0 to 1, okay? Then ReLU rectify the linear unit function. It's a simple shape. So once the x is larger than 0, then it just equals the x, the value, and otherwise it just becomes 0. Okay, we have 2 ways to define it. Then 10H, which is the hyperbolic 10 function. So it's related to the sine h and the cosine h. So if you are interested, I guess, yeah, you can search for related materials to check those details. So for simplicity, we just put the equations here. You will see what is the shape of the tan hx function is as a activation function. Actually similar to the logistic. The difference is that it moves okay. One difference is that the slope, the changing rate is different. So at the Taylor part, it become more like smooth, not that sudden change, and also move to the decision point to the origin instead of to the 0.05, 0.5 compared to the logistic function. Okay, actually there are many other activation functions that for different kind of purposes. So in this lecture, we just take a look at these three functions. So then here is the like a summary how we can select activation function in a neural network. So as you can see, depends on the problem types. So mostly in the hidden layers, we use ReLU as a hidden layer function, okay, activation function. In the last layer activation function, then can be sigmoid, softmax, and sigmoid. Mostly is sigmoid or softmax. Softmax we didn't put here, but actually similar to the sigmoid, a little bit different. You can check. And the loss function here, many of them they use the cross entropy. In our case, we use this MSE, right? Mean squared error, similar to our definition of the value function error. And yeah, so this is generally how you can choose the hidden layer or last layer activation functions. Depends on your problems type and the outputs, the final outputs. So then the universal approximation and deep neural networks. So as actually the 20 or 30 years ago, some people already proved that for neural networks, if you only have one hidden layer, if this hidden layer is large enough, so this hidden layer use the sigmoid units, then this kind of one hidden layer neural networks can approximate almost any can approximate a function with any the precision. Okay, so actually as long as you have enough this one hidden layers node unit, then you can approximate function with different kinds of position. Okay, so means that we call it the universal approximation property. But in practice, most of the time we use multi hidden layers neural networks. It provides multi-level representation, showing a strong expressive power. As shown here, this is the two hidden layers neural networks. It has the first and second hidden layers has 6 and 8 units or nodes respectively. Okay. So since this is a lecture, then let's just simply review how we can calculate or update the weight through the neural networks. So how we can train the neural networks with a gradient descent. So actually, I guess, so assume that we have this one hidden layer neural networks. Then we have the two input, S1 and S2. You can consider them as the what is that? What do we call it? The here the we divided into the so actually it's a vector of k numbers that represent the state S, right? It's based on the here. Okay, so So you can consider S1, S2 as a kind of different representations of the states. Okay, representation S1. So if you have states S, for example, you have S states S, then we use multiple like factors or information to represent this state. Then we define them as S1, S2 as the input for these neural networks. So inside of these neural networks, there's one layer. It has 3 units, X1, X2, X3. It's the representation, another representation of the input units. Then here we only have one output unit, which is Y1 hat, okay? So assume that we have now in general, for generalizing these neural networks, we define SI. So we assume that we have I. So these subscripts are the size of the matrix we are defining, we are facing. Okay, SI means that it is a vector with I elements. Okay, then Aij, which defines the matrix, the weight matrix for this from input layer to the hidden layer. We use Aij. So Ij defines the size of this matrix. It has I row, J columns. Okay. Then since actually this J need to be equals to the hidden layer's size, we will use Xj to represent. And then again, we define another matrix, weight matrix, which is Bjk, which has the size Jk. So the row size should be equal to the previous hidden layer size. Okay. Then the output is the Yk hat. So in this neural networks, we only have one output. It can has multiple the outputs. Okay. Simply here we define our loss function as the MSE, mean squared error function. Okay. So it's easier to calculate and to represent. Then we define the activation function in each layer. In hidden layer, the activation function is FA. In the output layer, it doesn't need to have the activation function. Mostly it just output the last layer's the result, like the probability. So, but here we just define the FB as the activation function for the output. Okay. Yeah. So then, based on the updated rule in SGD, our goal is to update this weight by doing the gradient descent, right? To do this partial derivative with respect to the weight. So similarly, so then I just give you the the shape of the updating the weight matrix here. So actually we're gonna derive those process in the next slides. Okay. So first of all, let's look at how we start from. So actually the process we are using to update the matrix, the weight matrix, is so-called back propagation algorithm based on the chain rule and those stuff. So we will take a look at them. So then, yeah, let's look at this, how we can calculate, update the weight once we have some one output compared to the true output. So if you consider the loss function here, so the Yk hat and the Yk, we just need to compare the estimate value of Yk to the true value of Yk. So what is the error between the two values? So our goal is this, right? So then we have this Y k, then what we need to do is that we just need to like do the partial derivative for the loss function with respect to the bjk, the output, the matrix, okay, the weight matrix. Then if you do the partial derivative, then we, based on the chain rule, we add this partial, the y hat k and partial y hat k. So you see here, we just put, since it follows the chain rule, then we just put them. It doesn't change the original value. Then what is the yk hat? The yk hat is equals to the output. The output is the fbxb. So since if you consider it's like the activation function, so the output is x times b with this the output, the activation function, right? Now we can just, now in this case, actually we are using we are defining another variable, theta equals xb. Then we just put this fb theta into this equation. Then we use the chain rule again. We put the partial theta k and put partial theta k again on top of this partial bjk. In this case, since the theta is defined as x times b, the product of xb, right? The hidden layers units times the matrix, the output layers matrix. Then if we do so now it's related to the b, the matrix b now. And we can do the partial derivative directly, since this is a linear combination of the hidden layer. Then it actually it equals xj. We can directly compute this value, xj, which is the hidden layer, right? So then we can just put xj here. Now let's look at the other two form. The first one is we do the partial derivative with respect to the yk hat. What is this? This is loss function to the yk hat, right? Then we look at loss function. Well, we define the loss function as the MSE. So then we can just directly calculate this partial derivative value, which is yk. I mean, since this simplified, so the 2 will be moved to cancelled by the 1/2. Then it would just directly equal to yk hat minus yk, right? So because yk hat is in the front, then just times 1, that we don't need 2 times. So then we can just replace here. Then look at in the center of this part, which is fb theta k, do the partial derivative with respect to the theta k. So actually, if you look at since this is the activation function, so, and this is output, look at here, this is output layer activation function. Actually, it just equals the input itself, which is theta k. So actually, because this is the last layer, the output layer, just equals theta k, okay? Then if you do the partial derivative, it just equals 1. So eventually we got this very simple, like straightforward shape, the yk hat minus yk times xj. So at the same time, we define this okay, the delta b, that we use another new term to represent the first 2 parts of this the partial derivatives, okay? So we use the delta b to represent them, then times x. So even though we already calculate this, but actually depends on the loss function, the calculation result can be different. In our case, we just use the simplified, the MSE, then the output is simple. But if you use another loss function, then we may be different shape. But without without loss the generosity, then we just use the delta B to represent the two parts. Okay. So just remember this. So how we can update the B matrix. Okay. So what we do is that with B minus alpha times the delta B times X. The delta B equals these two parts. This is the first the update process. This is the first step of the backpropagation algorithm. The next step, so we also need to update the matrix Aij here, right? So now we need to trace back from the output the units to the Aij. So let's continue this calculation process. Now we try to update this Aij. So Aij, actually we need to calculate from the output units and trace it back to the Aij. What do we do? Similarly, we can calculate, we start from here. Everything start from this loss function. Then we do the partial derivative with respect to the Aij. So this is direct operation, right? The output, from the output loss function from here, then we want to update the Aij. But the thing is that we cannot directly calculate with based on chain rule. We just put this partial yk hat, the intermediate variable. Similar to the previous one, we can now previously we defined this so the y this yk, so this partial derivative yk hat actually equals this activation function, which is xb xb, right? So we use theta to represent the xb, so which we just replace here, directly replace here, yk hat equals fb theta. Then we use the chain rule again, the partial theta k times partial theta k divided by the partial aij. Okay. Now this part is just exactly the delta kb we defined previously. If you look at previous definition, the delta b here, then which is exactly this part. Okay. Then we can just directly use the delta kb to represent this part. The remaining part is that theta k with respect aij, theta k is xb. You can just put xb here. Then actually the only x is related to the aij, because you look at here, the aij and xj, they have the relationship, right? So the bjk has nothing to do with the aij, so there's no direct relationship with them. So we can just direct move out the bjk out of this partial derivative. Now it becomes we do the partial derivative to the hidden layers units with respect to the aij. Now we have this shape, right? So you see the theta k. So theta k equals the xb. Then xb, since b is not related to this the matrix A directly, then we can move it out. That's the logic here. Now look at this shape. Okay, actually I already showed this how we can get this step, right? So from here to here. Now look at this shape. So we're gonna redefine the activation function in the hidden layer. So here we define the activation function FA. Now we use another term, which is psi, to replace the SA. Okay, we use psi j to represent the SA for simplicity, because we want to use the chain rule, right? Then based on the chain rule, then we can add this partial psi j here. So yeah. So similarly, so now we are having this since psi j we is equal to the SA, then we do the partial derivative with respect to the ij, which immediately equals to the SI, right? So now we just look at the other parts. So well, we already have this the delta KB is already calculated in the previous step. BJK is also it has the current values, so we don't need to worry about it. And the partial FA psi j do the partial derivative with respect to the psi j. With this psi j, so actually because this is a activation function, so depends on what kind of activation function has been used in the hidden layer. So for example, if we use this ReLU as a activation function, which is shown here, FA psi equals if it's 0, if psi is smaller or is less or equal to 0, then the FA psi is 0. Otherwise, it become just psi itself, which is ReLU, the definition of ReLU. If you put this ReLU to here, then you can directly calculate this partial derivative. In this case, actually, for the psi is greater than 0, it directly equals to 1, right? Because if you do the partial derivative, it only has one variable, then just equals 1. This part will become 1. But for the generosity, for generalization, so we don't directly put 1 here, since this activation function can be different case by case. So we just use another variable to represent this part. We use the delta A. Here I use the subscript to represent the size, okay? Delta JA to represent this part. Now we have the rule to update the matrix of input layers, the matrix, right? We use A equals A minus alpha delta AS. So all the components inside of delta can be calculated. Delta KB is calculated in the previous step. BJK has the initial information, okay? And this partial derivative with respect to this the available inside of the activation function for the hidden layers, okay? Now, actually, we are ready to design this back propagation algorithm in the neural networks for updating the weights. So this is how we can update the weights with one hidden layer neural networks. It's easier to extend to the multi-layer neural networks as long as you give some iteration, okay? So what we do is that for each data point sy in dataset D, so since actually since in the reinforcement learning, the data point is online, is generated step by step. In our case, so it means that the whole step, the whole process, we're gonna run these neural networks again. So the whole process, like each episode is step, in each episode, for each step, we're gonna generate trend, update the weight again and again. So what do we do? So I just rewrite the process here. So the delta KB equals this part we define, I explained. So then the gradient equals the delta KB times xj. This is the gradient, right? Now we use the SGD, the mechanism. So we use the B minus alpha B, there this Nabana B, okay, to do this the gradient descent. Okay. Now again, similarly, so for the next layer, then we already defined this delta JA, right? So one difference is that I switched the position of the variable. One is a delta KB, which is a vector with k element. So previously calculation, I just put delta, not delta, the sigma KB to here, okay? So since the BJK is a matrix, we need to move this sigma KB to after the BJK. So in this case, we switch the position, then times this the partial derivative to the activation function in the hidden layer. And similarly, we put this sigma JA to this here. Then this is a gradient. Then we use the SGD approach to update A. So then we just iterate this process for each data point. Then eventually those matrix A and B will be updated accordingly. And if we consider the different activation function, then it will be calculated easily. So for example, the output layer, it will just output directly what is the input for the output layer. Then for the hidden layer, we usually use the ReLU. So ReLU here, so the partial derivative of ReLU is simple. Okay, so this is how we can use the neural networks to learn to update the weights, okay, inside of the neural networks. And with this way, we can when we keep updating the weights inside of these neural networks, then depends on how you define these neural networks. The output can be the action, what kind of action, the action probability, if you consider the RL environment, based on the input, okay. It can also be depends on your definition, okay. Through this process, we can like approximate the optimal value. Okay, so we have talked about this, how we can update, how we can like train the neural networks with a gradient descent approach, okay. Now we move to these optimizations in neural networks. So as it has been learned that we are knowing that deep neural networks may cause overfitting issues, okay. So since if you don't just use the original like deep neural networks, eventually if you have multiple layers, hidden layers, eventually you will have a not satisfactory result. Also, the partial derivatives may decay rapidly, making learning slow or unstable. So because if we don't do depends on the scale of the input layer or those the features we are inputting into the neural networks. So sometimes when we do the partial derivative for some particular variables, it may reduce quickly. So once that happens, then when the value becomes very small, then the learning speed becomes slow. Or sometimes it just fluctuates a lot to make the learning very unstable. So there are several remedies. The first one is we do the cross-validation. By doing the cross-validation means that we're gonna stop training when the downgrading happens on some validation data set. This is one remedy, one approach. Second one is we can modify the objective function to reduce complexity. So generally we call it regularization. Then we add some bias into the objective function. So this kind of to sort of to correct or like put it back from the overfitting issue. The third technique or method is to add dependencies among weights, also called weight sharing. Sometimes you will see that in some design of neural networks, they can, for those weights matrix, some weight may be used, some weights we don't need to update. We just share one weight from the one particular input instead of calculate every weight. Then the fourth method is a dropout unit, means that we can design the neural networks by intentionally skip some units in the hidden layers. So it's like we drop out units when we update the weights. The fifth technique is batch normalization. So batch normalization is to regularize the input data scale, so make them into normalized. So with the normalization, then we can get the better performance. The last one, but not the least, is that we call it residual learning. Actually, it's similar to the dropout, but it's from a different approach. We can add skips in the neural networks, means that we can add shortcut connections. So it's like we have one. So if you assume that you have multiple hidden layers, then you can, instead of directly use those weight matrix to connect them, we can directly connect one, for example, the first layer hidden layer, the one unit from the first hidden layer to the third one unit, one unit in the third hidden layers, instead of updating the weights. Okay, with this way we can kind of reduce this overfitting and decaying issues. Other approaches, other optimization techniques are the weight initialization. So previously, in the previous the algorithm design, when we talk about this issue, so if you recall, you can check those slides. When we define these gradient Monte Carlo approximation algorithms, in the algorithm, when we want to initialize the weight, we just use for example, 0. So we didn't consider weight in actually the weight initialization. We just give the initial value as 0. So, but in neural networks, it's better to give the small initial random variable to weights. For example, we can use each connection to generate a small weight based on the normal distribution. Okay, but though we can have this weight in a small initial random variable, random numbers, but the thing is that if the input units, the size of input units is large, then it will bring another issue, because at the beginning, if your input size is large, then every input has the initial weight will contribute to the first hidden layer. Then it will bring the large variances in the first hidden layer, because the network hasn't been trained, but the first hidden layer already have a large number of contribution from the input layer. Then one remedy approach is that we can do the normalization again for those initialized random numbers. We can just divide the square root of the number of input units to the normalization, kind of reduce their size, the value again. So the next technique is update momentum. Actually, this technique has been used in those standard SDD process. Okay, if you check those PyTorch or the TensorFlow, those library, those packages, you will see it. They already have this momentum part in when you directly use their API, the SGD momentum part. Okay, by saying momentum part, we say that when we update the weight with the SGD, we intentionally add the one more part. We call it momentum. So this momentum will be updated based on the changing rate of the loss function. Okay, so with means that originally, so this red line means originally the SGD updating process. The momentum will be based on this changing rate of the SGD to define the a faster learning speed. Okay, in this way, actually, we can accelerate the learning speed. So this has been a standard techniques in the SGD, in the state of the arts, the approaches. Okay. So yeah, these are the information we need to know so far. So since we only learned the linear approaches and nonlinear approaches, which is neural networks, so perhaps we can, in the next lecture, we may take a look at some examples, how we can use them to do some actual work, to apply them for a particular application. So summary, so we have learned the feature construction for the linear methods. For building the features, we learned several basis functions, polynomials, Fourier basis, cos coding, higher coding, radial basis functions. So all these basis functions, they kind of generate a set of the, let's say, the feature representation. Then with those kind of feature representation, we can introduce some interactions among features, or we can introduce some extra benefits from those these kind of basis function. And yeah, so also as I mentioned in those basis function, when we define these function sets, we don't need to use them all. We can, based on our knowledge for a particular problem, we can just select a subset of them to be used. Then the last part is for we learned the neural net, how we can use neural networks for nonlinear function approximation. Okay, so to approximate the value function, then we recapped the basics of the neural networks, then how you can train the neural networks, and how we can design the backpropagation algorithm for updating weights. Then the last one is that we also reviewed some optimization techniques that have been used in the neural networks. So actually, I guess many of you already have been familiar with the deep learning. So if you use PyTorch, when you actually, since the backpropagation algorithms are kind of a deterministic, once you define the forward path, define the neural networks, actually the PyTorch, you just need to define the forward networks, means the structure of the neural networks. The backpropagation can be, once you train the neural networks, the backpropagation algorithm will be automatically run. So you don't need to care about the backpropagation. But for this learning purpose, it's better to understand the mechanism behind the thing. Okay. Yeah. So now, from now on, and you are ready to try to combine the deep learning with the reinforcement learning. Then it become a new area, a new field, so-called deep reinforcement learning. So yeah, so you can use different techniques from the neural networks to approximate the state values or the action values. So in the next lecture, we're gonna we're gonna study those instead of a prediction. Now we are moving to the control, parameterize the control function approximation from either linear method or nonlinear method. Okay. Okay, that's all. And yeah, hope you can get watch this lecture, and we may review these contents when I came back to Korea. And if you have any questions, you are welcome to send messages to me through the iCampus or send me email. So I'm happy to answer and try to solve the give you some suggestion. And also for the term project proposal, I will check those proposal and give you some feedbacks, especially whether those proposals are proper or not, or some parts you need to modify or need to consider some particular aspect in your term project. Okay, thank you for your attention, and see you later.